All right. Thanks, Jan. Right away, I'm supposed to play a video from Bar. So that's I'm going to play right here.
Served dozens of watershed organizations, some of them for more than 50 years. With our experience and innovation, BAR provides a science-based, multifaceted approach to water resource and watershed management. Working together, we can help you make a difference.
Welcome to the Minnesota Association of Watershed Districts annual conference, and thanks for joining us at our session. Although we are really looking forward to gathering in person, hopefully next year, we are glad we can at least gather virtually this year. In the next few minutes, we'll give a brief overview to BAR, introduce our upcoming presentations in this session and also later at this conference, and highlight a few of our newer senior staff. Of the more than 425 employees in our Minneapolis office, nearly 100 are engaged in water resource engineering and planning, stormwater, floodplain and wetland management, limnology, and landscape ecology. Our breadth and depth of experience offers watershed organizations peace of mind that we can provide an innovative solution to any water resource related challenge that we encounter. BAR has served as the primary consultant of 18 different watershed organizations in Minnesota, with some of these relationships dating back to the 1960s. And we have worked with numerous other watershed organizations across the state, region, and country. And we are excited to share some of these experiences with you today with our upcoming talks during this session. In one session, Senior Water Resource Engineer Greg Wilson will present pond treatment with spent lime to control phosphorus release from sediments. This presentation focuses on research done in cooperation with the Ramsey Washington Metro Watershed District, Vadnais Lakes Area Watershed Management Organization, and the City of White Bear Lake, and includes the evaluation of the costs for aerial chemical applications. In our second session, Water Resource Engineer Tyler Olson will be presenting What Does Climate Change Mean for the Future of Flooding in the Red River Basin?, where he'll be discussing a literature review conducted for the Red River Basin Commission as part of its long-term flood study update that looked at the impacts of climate change on the Red River Basin from an international scale all the way down to a local scale, and highlight some of the key trends and unknowns looking into the future. In the third session, Josh Maxwell from Riley Purgatory Bluff Creek Watershed District will be presenting water treatment byproduct used to enhance phosphorus reductions. BAR has assisted the district on this assessment, and this presentation will cover a discussion of several years of pollutant removal performance monitoring and modifications made to improve the system's overall performance. In addition to the vendor track presentations in the next hour, you can also tune into some additional presentations later this afternoon and tomorrow. At 2 p.m., Chad Engels of Moore Engineering and Greg Franson of Bar Engineering will be presenting the Red Path Impoundment and Mustinka River Rehabilitation Project. Working as a subcontractor to Moore, Bar provided geotechnical, structural, hydraulic, and wetland mitigation design services for a proposed 19,000 acre-foot flood impoundment and 5 miles of restored stream channel. Then tomorrow at 11 a.m., Dan Tix will present wetland restoration challenges in an agricultural landscape. Dan is a certified ecological restoration practitioner with over 20 years of experience and will discuss many of the challenges of wetland restoration in highly engineered agricultural landscapes. He has been working with the Shell Rock River Watershed District to complete several wetland restoration projects with goals to improve water quality, reduce flooding, and increase habitat. In the past few years where we've not been seeing each other as much as we'd like, we still have been growing our team capabilities and expertise, and we wanted to introduce you to a few of our newer senior hires. Marcy Bean joined the BAR in March of 2020 from the Mississippi Watershed Management Organization. As a senior landscape architect, she helps align water quality capital projects with beautiful and sustainable landscapes post-construction. Marcy specializes in facilitating complex project partnerships and incorporating operations and maintenance considerations early on in the design process to create a more successful project long-term. Stephanie Johnson, a senior water resources engineer, joined BAR in October of this year, serving as director of the Surface Water and Sewers Division of Public Works at the City of Minneapolis and as the Projects and Outreach Director at the Mississippi Watershed Management Organization. Stephanie brings a wealth of experience in the water resource management field, having worked with many of the Minnesota watershed districts and their partner agencies over the past 20 years. Her key service areas include watershed planning and analysis, grants, surface water modeling, feasibility studies, green infrastructure, and decision support. Chris Lenhart joined BAR as a senior water resources scientist and restoration ecologist. He has over 20 years of experience in research with the University of Minnesota and implementation of restoration projects geared towards water quality improvement. His experience in stream and wetland restoration and assessment of those practices for hydrologic, nutrient removal, and sediment load reduction benefits. He has worked with watersheds on treatment wetlands, stream restoration, and ravine stabilization projects around the Twin Cities and southern Minnesota. Joe Bischoff is a senior aquatic ecologist with over 20 years of experience helping Minnesota watershed districts with water quality and natural resource planning projects. Joe's partnerships with his watershed district clients resulted in measurable water quality improvements in local lakes, streams, and wetlands, as well as increased ecological health. Joe's work ranges from environmental chemistry to ecological assessment and restoration, including plants, fish, and everything in between. Again, we want to thank you for joining us at our session during the virtual MOD conference this year. We hope to see you all in person soon. In the meantime, we look forward to the virtual happy hour event starting at 4 p.m. tonight. So feel free to stop by the bar area of the happy hour event and do not hesitate to reach out to our staff with any questions or just to catch up. We're looking forward to seeing you there.
All right, so now I'll just get right into my presentation. I'd like to thank the City of Chanhassen for their partnership in this project. And I'd like to recognize Brandon Barnes from Bar Engineering, who was the main engineer for this project, but also Scott Sobiak from Bar Engineering as well. So today I'm just going to be talking about one of the water treatment systems that the Riley Purgatory Bluff Creek Watershed District has out in the field, and it is a spent lime treatment system. That photo is the post project completion, and then a little later on I'll show you some pictures after completion. But just kind of general outline for today, I'm going to discuss the site information, why we needed the spent lime treatment system there, what is spent lime and how it works a little bit, look at the treatment system design, how it functions, and then some of the issues and retrofits we put in place to correct those issues, and then work over a couple of years of results, kind of sum it up with some conclusions, and then we'll have plenty of time for questions. So for those of you that are not familiar, the Riley Purgatory Bluff Creek Watershed District is about 50 square miles, and it's located in the Southwest Metro. Primarily Chanhassen, Eden Prairie, and Minnetonka cities make up the Watershed District. However, it does include 7 other cities. And the particular lake of concern that I'll be talking about today, and where the project is located, is Lake Susan, which is within the Riley chain of lakes. Just a little background information on Lake Susan. It's a relatively small lake. It's only 88 acres. It has a max depth of 17 feet, and the direct runoff of the surrounding area is 66 acres with an upstream watershed size of about 1,200 acres. It's considered a eutrophic lake, and it is impaired for nutrients and mercury, which we have seen continuously. It's one of the more degraded lakes within the Riley Purgatory Bluff Creek Watershed District. And just to look over on the right, those 3 graphs, those are the big 3 MPCA water quality parameters to look at impairment status for lakes. The top graph is Secchi depth. So if it's below the line, it's meeting the MPCA water quality standard for shallow lakes, which is 1 meter. You can kind of tell that it's hanging right around that threshold. We have been meeting it recently. And then the second graph is the chlorophyll-a graph. And you can see since back in 1972, it's kind of just above the line for the bottom 2 graphs is not meeting the MPCA water quality standard. So, and their max and mins are also located on those graphs for each year. And all these are based on summertime averages. So from June to the end of September. And it has never met the MPCA water quality standard for chlorophyll. And then the bottom one there is total phosphorus. And again, most of the time it is above the MPCA water quality standard. Carp are under control in the lake. We've also done continuous herbicide treatments for curleaf pondweed. Some of the projects that have also occurred. So now I'm going to talk a little bit about the issue wetland that we were concerned with. So in 1996, Wayne completed use attainability analysis, which really dives into looking at the areas of concern around the lake and identifying project areas. And this was updated by BAR in 2013. And it identified that 67 pounds of phosphorus per year were entering Lake Susan from the wetland complex to the southwest. And this was the largest identified external source. And we looked at quite a few different options. A wood chip bioreactor and iron sand filter were considered for this project location, but mainly because of the contact times with those 2 other treatment facilities, the overall footprint of the project was too large for the constraints at the project site. So we needed to fit a smaller treatment facility in there because of the wetland, and there's a trail system that runs in there. And the spent lime treatment system, while very comparable removal rates allowed a smaller footprint, which is ultimately why the board decided to go with the spent lime treatment system. And again, we did partner with the City of Chanhassen. I'd just like to thank them again. So a little bit about what spent lime is. Basically, spent lime is calcium carbonate. It's a byproduct of drinking water treatment plants. Water is filtered through, and then as water flows through spent lime, phosphorus binds to the calcium and forms calcium phosphate, and then it just leaves the phosphorus behind. And although we don't really have a handle on exactly the lifespan of spent lime, its binding efficiency for phosphorus is really high. And just some other projects have indicated it's got a very long lifespan. And then I just wanted to kind of show the pictures of how we get the spent lime. It can be in larger clumps also, but the pictures to the right are compared to sand. So now I'm just going to kind of walk through the spent lime treatment system. So starting off to the right, that's just a picture of the wetland. There was already a culvert going under the recreational trail that I talked a little bit about, and then that drains through another wetland creek area into the lake. So we already had a manhole access point to take our inflow samples, and we essentially tapped into that and redirected about 56% of the annual flow via stop logs in the picture, the second picture there. We could manipulate how much water flow we wanted through the system. And it was estimated that about 65% of the total phosphorus would be removed from 56% of the flow through that system. So now kind of taking a look inside. Once the water enters into the spent lime treatment system, which is essentially a concrete box. It's 25 feet by 10 feet. And then there's a layer of about 1.3 feet of spent lime material, and then pea gravel on the bottom. And then within the pea gravel is a perforated drain tile to drain the water. Water leaves and goes into the outlet manhole cover where we grab our outlet samples. And then there's a backflow preventer that allows so the water doesn't back up into the spent lime system. And the contact time for spent lime is about 5 to 10 minutes. I kind of mentioned that earlier. The other BMPs we looked at, those contact times were around 30 minutes. So it's a quick contact time with the removals. And then over the top is a graded panel that can be removed, and we can climb around inside and fix whatever needs to be fixed. And then that's just a picture inside. Directly below there is a picture inside of what it looks like when it's all filled in. So as I mentioned, there's a backflow prevention device, and the discharge rate is about 0.2 cubic feet per second. And then, so we put the project in and everything worked absolutely perfectly. Well, as with newer BMP technologies, we did have some issues. And now I'm going to kind of walk through the issues and how we attempted to correct them or corrected them, and just how it's worked overall. So the issues are highlighted in red, and then just kind of what we did is below. So one of the things we ran into was the system short circuiting. We did have different holes cut into the system that were maybe allowing the system become leaky. And then also the corrugated under drains. I showed up to the unit one day and we had a trench basically forming in the unit. And basically the corrugated pipe had become detached from the main stem drainage pipes. And so we replaced those with hard PVC and then shored up those connections. And then we fixed all the other leaks, potential leaks that we deemed necessary. So, and then one thing we did notice was we would show up there and there'd be long extended periods of inundation, more so than what the system was designed. So we needed more control in our, just more control of the water. So what we did is we did a couple things. We installed a solar powered lift station. Those are the two bottom pictures there. Well, actually it's all three of the pictures there. Basically this allowed us to reduce the system operation so we could really pinpoint and make sure our system was efficiently performing. So what we ended up doing is running it Monday, Wednesday, Friday from 8 to 5 o'clock. And this just basically lifts the gate and then shuts the gate during those times, and it can be set up scheduled. And then we also added that big red lever, which essentially allows us to shut all flow off to the system. So one of the bigger issues that we did run into was the compaction of the spent lime material didn't allow for filtration and ultimately nutrient removal. So after long extended periods of inundation, the spent lime material packs together real tightly and almost eliminates flow through the system or severely reduces it. So what we decided to do was look at something we could mix with the material to improve filtration capacity. And so we decided to do mix sand with it. So we tested different types of sand. So just regular sand that you can get anywhere, wash sand, plaster sand, and pool sand. And then we did different mixes of that. So 50-50, so 50% the sand, 50% spent lime, 70% sand, 30%, and so on. Just to see. So we set up this experiment, column experiment in the lab with these different mixtures, and it allowed us to capture what was happening. So we were looking at two main things, obviously removals, but also the ability of the water to move through the material. So what we did was we flushed water through the different mixtures periodically after remaining stagnant for up to 114 days. So that graph on the top right, basically the bottom, the x-axis there is the days, and then the TP % reduction. And you can kind of see, we ultimately decided to go with the 70-30 mix because it performed just as well as the other mixtures. So, and then on the bottom graph right below that, again, days are on the bottom, and then that's how much time it took for the water to flush through the system. So basically we set up the columns, we put water in it, we flushed each of the columns a bunch of times, put water in it, let it sit for that number of days. We'd let that water drain out, and then we'd take fresh water from a wetland and compare the pre and post, how fast it went through, and then the phosphorus that was pre and post. So like I said, and then on top of that, we wanted to really see if we continuously ran water through, if any of the material would migrate through the sand, the spent lime material, and compact on the bottom. So we wanted to know that as well. So we set up two columns, 70-30 and 80-20 sand spent lime mixture. We allow it to continuously run. So we put a pump in there and just let it run for 54 days just to make sure our filtration capacity wasn't reduced. And kind of the overall conclusions we got was 70-30 seemed like it performed the best. Sand is really dirty. So make sure when you're doing projects like this, you're comparing. Even the wash sand that we utilized at first was incredibly dirty. So, but we found some good washed sand, and we ultimately went with the wash sand. Pool sand is what we tested a lot of our columns with. But if anyone knows the cost of pool sand, it's extremely high. So now I'm going to kind of get into some of the results. This is the 2020 and 2021 total phosphorus removal efficiencies. So on the bottom is the date, and then the the bars there in the middle are the phosphorus. So the inlet phosphorus is the total bar. It's the blue and the orange. And then the outlet phosphorus is in blue. And that is basically what is leaving the unit. So you can kind of look at it that way. So in 2020, well, as a general trend, what we see is at the beginning of the year, it starts out low. The removal efficiencies are low. And then as the summer progresses, and I mean, ultimately phosphorus levels are higher in July and August, the removal efficiencies improve, which may explain some of that. And then in the fall, it does taper off a little bit. I'm going to show you another graph here to kind of show it a different way. So this is just percent reduction. So how much phosphorus was removed. And in 2020, we got, you know, that in mid-July, we had up to 95% removal efficiencies. And again, kind of like I explained, both years, it started slow, performed well in the summer, and then kind of tapers off in the fall. And averaging across, we had 62% reduction. So right at that 65% expected reduction that we assumed was going to happen. And in 2021, we did have a reduced capacity, so 41%. One thing, I'm going to back up here for a second. One thing I just wanted to point out is the total phosphorus values on the y-axis. If you're just looking at how high, these are incredibly high total phosphorus values. Anywhere, they're extremely high. So it kind of indicates that maybe our UA was underestimating the amount of phosphorus in this location too. So I just wanted, we didn't just monitor total phosphorus, we monitored chlorophyll, total suspended solids, and then we broke phosphorus up into total dissolved phosphorus and orthophosphorus also. So different forms of phosphorus. Again, across the board in 2020, we had 50% reductions across all those different other parameters we measured. And in 2021, you can kind of see orthophosphorus, chlorophyll remained relatively the same percent or reduction of efficiencies, but total dissolved phosphorus and total suspended solids were reduced, but it is performing. So kind of just overall, in general, conclusions is check your source materials and expect initial flushing. Again, sand is dirty, so make sure you're getting the best quality sand that you want for your project. And even if you're getting really good sand, it's likely that you're going to have some initial flushing anyway. So just be aware of that. And then it is critical that the spent lime material is allowed to dry out. Again, we saw that long periods of inundation cause the physical properties of the media to prevent filtration. So we need to allow it to dry out. So having that control is good. The water control is good. Occasional mixing or fluffing of the spent lime is needed. We mixed it once in each year, and we may increase the mixing. And this eventually or essentially is preventing the material from compacting and then breaking up the preferential flow paths that are forming within the material. We also have looked at different ways of mixing. Currently, we're just mixing by hand, but we're also looking into that. And then kind of like what I talked about earlier, the incorporation of gates and valves for on-the-fly adjustments to improve overall system performance really helped us in this project and was necessary and should be considered when putting in BMPs. And then overall, the spent lime treatment system works. It removes phosphorus and other nutrients. We believe that since the phosphorus levels coming out of that wetland are so high that maybe the system is overloading and not allowed to remove as much phosphorus as we were hoping. But this is only 2 years of data, and next year we'll really be able to see what's happening. So additional treatments of the wetland might be needed and probably will be needed to address the nutrients just within that wetland, just because they're so incredibly high. We did map the wetland and we were looking at different avenues, maybe an elm treatment or something like that to address some of those high phosphorus levels. And then with that, hopefully I did a good job. But if there are any questions, I'm open to any questions. I know Brandon's available also, so.
So can we just speak up or what? How does this work?
Yeah, go ahead.
Okay, Josh, so did the drought affect the flow? I mean, would that have been a consideration with some of the issues here?
Yeah, so we did have a period in August where we didn't actually have any flow through the system, but it was a short window. Even with how dry it was, we can play with the stop logs within the inlet manhole and push water into the unit kind of regardless. So yeah.
Hi, Josh. I was actually wondering, how long is this typically inundated? I see that the inflow is connected to the wetland complex. So do you have is the flow into the system fairly continuous for multiple days after rain events, or does it tend to be more sporadic?
Yeah, so initially what we had set up was almost like a continuous flow through the system, but then we put in that solar powered gate to open and close it. So as I said in the presentation, we set it to only open on Monday, Wednesday, and Friday initially while we kind of figured things out. And it was open from 8 to 5. So it was set on that schedule through, from May to October, just so we could control the water flow through the system. So.
Got it. Thanks for clarifying that. And,
yep.
Does a period of inundation, you guys suspect that affects performance? Like, is it the drying period critical?
Yeah, at least we believe so. Yeah, that it was impacting, but more so it was just when we had all the material within just spent lime, so 100% spent lime, no sand mixture. When we had those long inundation periods, it was just compacting and basically forming like a clay type sheet, not allowing filtering to occur. More so than running it continuously after the sand is put in, which we might try eventually, but currently we just have it set on that Monday, Wednesday, Friday schedule.
Josh, Grace from 9 Mile. I was just wondering what the shutdown or operations are in winter months.
Yep, so we do take the system offline in the winter. Basically, we turn the red valve to shut all water flow off in the unit, and then we lift the solar gate up, and that's turning it off so it's really quick and easy to turn off and turn on. In the spring, we'll turn it on pretty quickly after temperatures get above freezing and we actually have flowing water. So.
There are a couple questions in the chat. The first says, I believe you had the 2020 and 2021 summer nutrient data up on the slide, and there were no drastic improvements to lake water quality yet. How long do you plan to monitor to try to determine the impact?
Yep, so Lake Susan, okay, so first we are going to monitor this treatment system continuously for a while. But kind of like I addressed in the conclusion side there, the system is performing, but it's not capturing the phosphorus levels coming out of that wetland area are extremely high. So other issues, other things we're looking into is potentially an alum treatment for inside that wetland to treat some of that. We have looked at some other options too. Lake Susan also has pretty high inputs from Lake Riley Creek upstream. There's a stretch right now that we're in the process of, we have a project in place to do some creek restorations up there. And then there's a stormwater pond on the upstream side of the lake also that we put in a bench in partnership with City of Chanhassen also. We put in an iron sand bench there also. So yeah, so with all those different projects being put in place, we're hoping that we are going to be seeing improvements in Lake Susan water quality pretty soon.
And then the next one is, are these grab samples, and when are you collecting these samples, during or after a storm event?
Yep, so these are just grab samples. They're grab samples from the inlet and the outlet within those manholes upstream and downstream of the unit. And then these are just random grabs when the system is operating. So we're not including the storm events in the system unless it happens during that the windows when it's operational.
Okay, and another, was there a specification for the spent lime, or are all the spent lime sources, drinking water treatment plants, fairly similar?
I guess I'm not too unaware of that. I don't know if Brandon, if he's available for that question.
Yeah, of course, we did have a spec for the spent lime material. We worked with St. Paul to get our material for this project. We did look at other sources for the spent lime material, Eden Prairie being one of them. The reason we ended up going with St. Paul is that their the material from their plant comes as a solid, as a cake, that we could then mix with the sand and then use to develop this filter media. Whereas other systems, it comes as more of a slurry, and so we wanted to avoid that type of material.
There's another question. Do you have a guesstimate for how long the spent lime will effectively function before needing replacement?
Yep, that's a good question. These spent lime treatment systems, there are a few more of them in place now, but we're not exactly sure. Like I said, the kind of pre-studies indicated 100+ years, but we really don't know how long it'll last. And then specifically within this system, the high levels of phosphorus in that upland area may reduce the lifespan also. So we're really not sure, which is another reason why we need to continue to monitor this system.
I'm not seeing any other questions pop up in the chat.
All right.
So.
All right. Well, thank you guys for listening to my presentation.
Yep. Thank you, Josh. And we'll continue. We'll start up again at 10 o'clock. Thank you.